going to study about the crystalline defects or imperfections in crystals. Both are same, the crystalline defects or imperfections in crystals. The main cause for this crystalline defects, the main cause for this crystalline defects one second. The main causes for the crystalline defects is due to improper solidification. What is meaning by the solidification? The process of cooling the liquid metal to the solid state in different cooling rates. If that solidification process is not proper, then the irregular arrangement of atoms or some defects will be occurred inside the solid. Due to that, the defects will occur. And these defects are classified as point defects, line defects, surface defects, and volume defects. What are they? Point defects, line defects, surface defects, and volume defects. And point defects is also called zero-dimensional defects, and line defects is called one-dimensional defects, and surface defects are called two-dimensional defects. And what is this? Why we call it as point defects or zero-dimensional defects? In this, the imperfections or the defects occurred in solid due to the improper arrangement of one atom or very few atoms. That's why we call it as zero-dimensional defects. And in line defects, it is a misplacement of a group of atoms or a planes in solid, so we call it as line defects. And in planar or surface defects or two-dimensional defects, in this case the planes are misplaced, a group of atoms are rearranged, or the different foreign atoms are added to the solid, and it is two-dimensional defects. And volume defects, it is a combination of two or more above mentioned defects. It is combination of point defects, line defects, or it is a combination of surface defects or line defects. So it is a combination of defects in a small amount of lattice area, that is volume defects. In detail, we will see one by one, that is point defects. And the point defects are occurred mainly due to improper solidification process. In this, only one atom or maybe few atoms are misplaced, or it can be replaced in structure, that we call it as point defects. Again, the point defects are subclassified as vacancy, interstitial, or in interstitial again sub-interstitial impurities or self-interstitial, or it is called substitutional impurities. So what is vacancy? Now you can see here the first arrangement of atoms here in the structure. See, one atom is missing. Okay, that means it is removed from the assigned location by giving off some external attractive force, and that will be removed. And you can see that we have vacancy, the empty space. So this is called vacancy. If this vacancy will occur by removing of one atom. Now you can see again the vacancy having two types, that is Scotty defect and Franke defect. And you can see the vacancy initially here, the atom one ion is removed, and this ion, you can see the representation, the big ion is represented as negatively charged and the small ion is represented as positively charged. And the positive charge because of losing electron, the negatively charged because of gaining of electron. And in this you can see, first I removed the negatively charged ion and later I removed positively charged ion because I need to balance the energy in the solid. So I removed both positive ion and negative ion to balance the charge in the solid. Then we call it as Scotty defect, that is Scotty vacancy defect. And if instead of removing here, what happens, the positive ion, you can see this Franke defect, the positive ion, the dotted portion, the positive ion, because of thermal hesitation or internal repulsive forces, because of thermal vibrations and internal repulsive forces, the atom is exaggerated and it was escaped from the assigned location and it occupies the unutilized space. The space is called interstitial space. The space is called interspatial space. The space the exaggerated and escaped ion occupies, this interstitial point or the space, and because of this the charge will not change, the charge will be balanced, but it will not be assigned in a assigned location. And this defect is called Franke defect. This defect is called Franke defect, and these are the classifications again under vacancy defect. Vacancy defect may be a Scotty defect or it may be a Franke defect. And next we will see interstitial impurities, or let me go to the next one. Substitutional solid solution. What is meaning by the substitutional solid solution? Now you can see this third figure. See, the green ones are the original atoms arranged, but you can see the blue one here. After solidification process, again I am subjected to the heat treatment process, and at the time I replaced this original atom with the foreign atom. Foreign atom may be of same atom, or foreign atom may be a different metal atom, can be placed. And in this case, because of reducing in diameter and the attractive forces between the atoms will be reduced because of the lattice distance. What is the lattice distance? The distance between the centers of two atoms or adjacent side or surrounded atoms is decreases, and because of that the charge balance will be it becomes unbalanced energy, and due to that we have a defect that is called substitution impurity. So then if it is instead of small atom, if I placed the larger atom, instead of here you can see it is a small atom, but instead of the small atom, if I replaced a large size atom, then what happens? it pushes it pushes away the surrounded atoms. Again, because of that, again the disturbance will create internal in the internal structures. Because of that, again the dislocations will take in place. That is also a one type of defect. The substitutional defect may be occurred because of the small atom, replacement of small atom or larger atoms. The atoms may be from the same metal atoms, or the atoms may be a different metal atoms. This is called substitutional impurity. Okay, and next one is interstitial defect. In this, the atom from the regular structure is removed, and or the foreign atom is added, to the existing structure, and the foreign atoms are occupies, you can see here, occupies the interstitial space. What is meaning by the interstitial space? The space is existing between the atoms after bonding. The space existing between the atoms after bonding, that space is called interspatial space. Then foreign atom will occupy that interstitial space, and it was attracted by the surrounding atoms. What happened? Because of adding the new atom without removing or adjusting the lattice distance, it creates the disturbances, and it try to attract the surrounded atoms. Due to that, the atoms try to hesitate or exaggerate from the assigned locations, and it try to move here and there. It try to occupy, so it jumps from one place to another place, and it creates the internal structure disturbances, and this is called interstitial defects. So what are the three types under point defects? Vacancy. Under again vacancy we have Scotty defect and Franke defect, and substitutional defects and interstitial defects. The three are falls under the point defects. The point defects is also called zero dimensional defects. Zero dimensional defects. Next we'll move on to the next defect, that is line defects. The majorly these line defects are occurred in the form of dislocations. The line defects are occurred because of dislocations. How these dislocations will occur? By adding of a row of atoms in the existing structure. The row of atoms will present in a plane. That means we are adding a new plane to the structures. Now you can see this. Every line is representing one plane, and this is one plane, and this is one plane, this is one plane. Every plane is having a series of atoms arranged in order. And if instead of, so you can see this diagram here. Here we have added a new plane here above this point. We have added a new plane to the existing structure. Because of that, the dislocation will take place, and in detail we will see that dislocations are again classified as edge dislocation and screw dislocation. The dislocations are classified as edge dislocation, screw dislocation. Okay, and you can see this edge dislocation. Now you can see this diagram. In the bottom I have a series of atoms. Count this: 1, 2, 3, 4, 5, 6. Now I'm taking another plane now. 1, 2, 3, 4, 5, 6, 7. So what happened here? Above this plane, a new plane is added. You can see this dark one, a plane is added here above this plane, and because of that the new atoms are induced or added here. Because of that the dislocation will takes place. What happened to these edges? You can see extended. And if this plane is added, if this plane is added above the slipping plane, then we call it as positive edge dislocation. A plane is added above the dislocation, above the slipping plane, we call it as positive edge dislocation. If instead of this, if plane is added, if plane is added below the, sorry, if plane is added below this slipping plane, then we call it as negative edge dislocation. Above the slipping plane is called positive dislocation. Below the slipping plane, we call it as negative edge dislocation. Sir, what is the slipping plane? The slipping plane is nothing but the plane at which the deviation or the deformation, at what plane it starts, that plane we take it as slipping plane. The initiation of deforming plane, then we call it as slipping plane, the starting deformation plane. Okay, and now important one, and still it is also a edge dislocation. And in this you can see I have drawn a circuit. I have drawn a circuit from point atom to atom, from atom to atom, and I found a gap here. I found a gap here, and the circuit is not completed here. And what is this circuit is called? Burgess circuit. The Burgess circuit is a circuit from forms joining of atom to atom along the plane. It may be a under defects or it is a pure metal. If it is a non-defected metal, it is a non-defected metal, then the circuit will complete. It joins the end to end. We'll get complete a closed circuit. If circuit will opens, it having a defect. So how the defect, the distance of defect will be measured or mentioned by using Burgess vector. What is the Burgess vector? The distance of magnitude, the distance and magnitude of a circuit, we call it as Burgess vector. The Burgess vectors is gives the information about how much magnitude or how much the distance of defect is present in the uh, solid due to defect, that we can calculate in using Burgess vector. And the circuit drawn from atom to atom, we call it as Burgess circuit. And to remember, the plane is added above the slipping plane, we call it as positive edge dislocation, and represented as inverted T symbol that I will show you here. You can see here inverted T, and this is a symbol for positive dislocation. If the plane is added below the slipping plane, then we call it as negative dislocation, represented as T. Represented as T. This is about line defects. The line defects are edge dislocation. And now, sorry, and next one is screw dislocation. In this, what happened? In this, the two slipping planes. In this, we have two slipping planes, and the two planes are perpendicular to each other. In the screw dislocation, we have two slipping planes, and the two slipping planes are perpendicular to each other. And if you draw a circuit along that slipping portion, and you can see a unclosed circuit. It just look like a small screw shape, so we call it as screw dislocation. Screw dislocation. In this, the two planes are dislocated and two planes are perpendicular to each other, then we call it as screw dislocation. Okay, and this is also occurred because of addition of new planes in different orientations. This is screw dislocations. Okay, and you can see, and now we are applying Burgers vector or circuit to the screw dislocation, and you can see the Burgers circuit starts from here, and I'm joining atoms from atom to atom, atom to atom. Once it reaches to the initial point, it does not closes. It shows some gap, and the gap will be represented as Burgers vector, and it indicates about the magnitude and the distance of the defect present in the solid. This is about the screw dislocation. And the next defect is surface defects. And the surface defects, you can see here, the surface defects is due to, also called two-dimensional defects. In this case also, a set of atoms are removed or misplaced or additionally added to the existing structure. What happened? Removing or addition of replacing the new set of atoms in the structure, the surface defects will occur. And the surface defects occur because of, or again, the surface defects are classified into three types. That is, one is stacking faults, number two, grain boundary defects, and three, twin boundary defects. What are they? Stacking fault, grain boundary defects, and tilt boundary defects. And first, this slide is representing stacking fault under surface defects. And now you can see the order CBA is one set of planes. C, you can see this order. In the first case, A, this is proper sequence. Did you find any missing of a plane? No. CBA, it is completely in order. Now, if you see the second diagram, C, B, A, C, B, A. It is in this case also, we have an order of planes. But if you consider the C plane, a set of atoms are missing from the assigned locations. Because of that, the stacking fault will occur. Sir, what is meaning by the stacking? What is meaning of stacking of an atoms? The stacking of an atom is nothing but the attraction of atoms, from one plane of atoms to another plane of atoms. Say example, I'm taking B plane. The B plane is a set of atoms. These atoms are attracted by C plane and these atoms are attracted by the B plane. Suppose, if you see in the second one, some C atoms are missing, and two ends, at right end and left end, both ends, the atoms are missing. What happens in this case? The atoms present here in A, this will be attracted directly by B, and in this end also directly attracted by the B atoms. And because of increasing in lattice distance, the attractive forces is decreases, and because of that attractive forces decreases, the strength of the material decreases. the strength of the metal decreases. So to that's why we are considering these stacking faults. Again, these stacking faults we have two types, that is intrinsic static faults on eccentric static faults. Intrinsic static faults means you can see here in this figure in the B row you can see the atoms are missing in the middle portion of the plane, and see A and C now they are attracting each other, and because of you can see instead of assigning locations the atoms are getting excited, exaggerated and attracted by C and A instead of B plane because there is no atoms are present at that point. Now you can see eccentric. What is eccentric? The atoms are misplacing or removed from the assigned location. B, you can see only in the center position we have an atoms, but at two ends of the plane the atoms are removed. No atoms are presented. Because of that, you can see the actual position of C is varied. Instead of straight line, it is bended into different orientations. So this is eccentric fault. In eccentric, the two ends of the atoms are removed, only center portion of atoms will present. And in intrinsic, only the center portion of atoms will present. Sorry, center portion of atoms are removed and both ends of the atoms will present. This is called static fault. Static faults. Next, we will see grain boundaries. Okay, in this you can see it is one grain, 2 and 3. If the grain boundaries in the grain boundaries are joined by different orientations, different orientations. If that orientation, if that orientation is more than 10 degrees, then that orientations and is called low angle boundaries. If the orientation defect is less than the 10 degrees centigrade, then we call it as low angle boundaries. If that tilt angle is more than 15 degrees, then the boundaries is called tilt boundaries. Is called tilt boundaries. What is low angle boundaries? The orientation, you can see here, the orientation of joining these grain boundaries, if the degree is 10 degree below the 10 degrees centigrade, the orientation is called low angle orientation boundaries. If the orientation is angle is more than 15 degrees, that orientation is called tilt angle boundaries. Tilt angle boundaries. Okay, and in all the crystals the boundaries will be oriented in different angles. It will not be on the same orientation. So that's why the crystals are rarely perfect. Because of that, even though you are giving a proper solidification process and you are taking care of removing all impurities from the material, even though the crystals are formed and joined in different orientations, the grains are formed and joined different orientations. So that's why the crystals are rarely perfect. Okay, and next one is twin boundaries. Twin boundaries. Now you can see, and in this is this plane, this is one plane, this is one plane, a set of atoms, and the middle we have another plane, and at the end we have another plane. The three planes are joined completely with the mirror image of the original tilt angles. Say example, the first one is joined to this with an angle of 90 degrees, with an angle of 90 degrees of tilt, and now the last one will be joined with an angle of 180 degrees. That means the orientation of the grains will be completely a mirror image. Okay, that and here whatever the major plane present in the middle, which allows to join the other planes on both the ends. The plane which is present in the middle and allows the other planes to join in different orientations, almost the mirror image of angles, then we call it as tilting plane. Is called tilting plane, and the mirror image planes are called twinning planes. The mirror image planes are called twinning planes. The last two planes are called twinning planes, and the middle plane is called tilting plane. Okay, this is about twin boundaries. Okay, and last one is volume defect. The volume defect is nothing but it is a combination of defects. It is a combination of point and line defects, or line and surface defects, or combination of all in a very small volume. In a small volume, that is called volume defect. And these defects majorly occurred because of this casting process and forging process, any some other production process. These defects are occurred. So these volume defects are uh, affect the major properties of the component after manufacturing. And these are the some of the crystal defects which related to the solids. So what are the defects? The defects are point defects, line defects, surface defects, and volume defects. Again, under point defects we have vacancy, interstitial defects, substitutional defects. Again comes under line defects, we have edge dislocation and screw dislocation. And comes to surface defects, we have stacking fault, grain boundaries, and twin boundaries. Okay, these are the major defects that we will consider while studying the crystal defects. It is also called imperfections in solids. Imperfections in solids. Okay. This is about. So, you have any doubts regarding to this? You can ask.
Once again, volume defects.
Volume decades. You want me to explain again?
Yes, sir.
Okay. The volume defects are the combination of point defects, line defects, and surface defects. Or it may be a combination of only a point defect and line defects, or it is a only combination of point defects and surface defects in a small volume. If you consider if you take a total volume, I mean total solid, in a total solid, if you consider only a small volume, in the small volume area we have a set of atoms, and in that we have combination of point defects. Like point defects, you can say vacancy, I have Scotty defect, and also I have screw edge dislocation defect. The combination of three or two or more than two, we call it as volume defects. Generally, these defects will occur when the solids are subjected to machining process or casting process or forging process. Okay, is that clear? Who asked that at
Sir.
me?
Yes, sir.
Okay. Any other doubts? Anything you want me to repeat, or anything you would like to ask regarding to this defect? You can ask.
Sure.
Sir, again, can you explain about the bulk vector, sir? Bulk vector.
Birth vectors. Okay, very good. I will explain. Yeah. Okay. The circuit. Now you see, I'm starting to draw a circuit from joining of points. So this is my starting point. 1, 2, 3, like that. I have continuing the joining of atoms, and one comes to the initial position. It is supposed to be joined. Why this will not be joined? Because of the addition of a set of or row of atoms, we had a gap. So this gap will be identified or represented by Burgers vector. And this Burgers vector is nothing but it gives the information of the distance or the magnitude of the defect. By using this vector, I can calculate or I can find how much defect distance or what do you call it as the variation in the lattice points that we can calculate or identify by using this Burgers vector. It helps us to represent. If anyway we need some a to represent, isn't it? How the defect will be, how much distance the defect is present in the crystal, and how much magnitude it varies. It shows in the defect that we need to mention, that can be mentioned by using Burgers vectors. I think you know what is a vector, isn't it? Yeah.
Yes, sir. Yes, sir.
So by using that we will represent it. Is it clear?
Yes, sir. It is clear, sir.
Okay. Any other doubts? Anything you want me to repeat, or anything you like to ask? You can ask. Yes. Somebody is posted that please check the waiting list. Hmm? See, when I a number of times I mentioned in the mail, please join the meet at least 5 to 10 minutes before, or else at least on the at same time. Even I'm starting the class 5 minutes late for the actual commencement time. Even though people are not able to join the meet, our time is very less. It is only 45 minutes is given, so we have to utilize the time properly. If I check the list continuously, the people are keep on adding to the list. It was just like it disturbing the class. It will not be allowed. Please join the classes at least 5 to 10 minutes before, or at least at the same time. Even I'm giving the 5 minutes of grace time to join. Even you are unable to join, so it is even nothing but we are wasting time. If I'm looking continuously for adding, how much time I will spend on this adding the request. So please join the classes before the commencement of time. Even every mails I'm mentioning, please join the class at least 10 to 15 minutes before, isn't it? Hmm? Who written this message to me? Keshav.
Sir,
Uh, who at the time who will be Who is waiting for the permission to join?
Meghana, sir.
Tell her to join at least 5 minutes or 10 minutes before.
Okay, sir.
Okay. So, is that clear now? Any doubts in the today's class? Yes or no?
No, sir.
If it is no, then I will move on to the next topic in the next class. And meanwhile, I will take the attendance. And after responding to your numbers, you can leave and you can join for another meter. No need to wait till I'm closing the session. Okay? Once you responded to your number, you just log into the next meeting. Yeah. Please respond for attendance. 61. 61. All of you, please respond for your attendance. 61. Okay. 62. 62. 62. 62 is Vikas.
No, sir. 63, sir. I am.
Okay. 63.
Present, sir.
64.
Present, sir.
65.
Present, sir.
66.
Present, sir.
67.
Present, sir.
68.
Present, sir.
69.
Present, sir.
70.
Present, sir.
71. 72. 72. 73. 74.
Present, sir.
73 is present. Vamshi, you are
Yes, sir.
70, 73. Right? Okay, 74.
Yes, sir.
74. 75.
Present, sir.
70.
75 present.
Okay, ma. 76.
Present, sir.
77. 77. 78. 78. 79.
Present, sir. 78 present, sir.
Okay, ma. 78.
78 present, sir.
79. 79.
Present, sir. Present, sir.
Okay.
Sir, sir,
80.
74 present, sir. Mike Panjatlan restart చేస్తా, sir. Sir.
Okay, ma. I will consider.
74. Yes, sir.
Okay. 79 is present, isn't it? 80.
Present, sir.
Yes, sir. Present, sir.
Okay. 81. 81. 82. 82. 83.
Present, sir.
83.
Present, sir.
Who is 83?
Sir, present, sir.
84. 85.
Present, sir.
Who is present? You are continuously telling. You are 83. Okay.
Yes, sir. 83 present.
Okay, ma. 84.
Present, sir.
85.
Present, sir.
86.
Present, sir.
87.
Present, sir.
88. 88. 89.
Present, sir.
90.
Present, sir.
91.
Present, sir.
92. 92.
Sir, present, sir.
93. 93. 94.
Present, sir.
95.
Present, sir.
96.
Present, sir.
97.
Present, sir.
98.
Present, sir.
99.
Present, sir.
A0.
Yes, sir.
A1.
Present, sir.
A2.
Present, sir.
A3,
Present, sir.
A4,
Present, sir.
A5,
Present, sir.
A6,
Present, sir.
A7,
Present, sir.
A8, A8, A9,
Present, sir.
B0,
Present, sir.
B1,
Present, sir.
B2, B2.
B2 present, sir.
What's your name, B2?
Bindu Bhargavi, sir.
B3,
Present, sir.
B4, B4, B5,
Sir, present, sir.
B6, 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 B7,
Present, sir.
B8,
Present, sir.
B9, B9, C0.
Present, sir.
Okay. See you tomorrow. You can join the next session.
Sir, you'll share the notes, no, sir.
Yes, ma.
Notes share చేస్తాను కదా.
I will send you that all PPTs of this unit after completion of the unit.
Okay, sir.
Right.
Thank you, sir.
Right.
Thank you, sir.
Okay.